All right, fellow knowledge seekers. Have you ever, questioned your pre-workout ritual?
Uh,
Specifically, that stretch you do, maybe hoping to fire up a different muscle group.
right, antagonist stretching.
Exactly. We're talking about antagonist static stretching, hitting one muscle to boost the performance of its opposing partner. For years, athletes have kind of debated this. Is it a secret weapon or, just a waste of time?
It's a common question.
Well, today we're diving deep into some brand new research that throws a powerful spotlight on this exact question. Our mission today is to really unpack a fascinating new study. We're delving into an article titled The Acute Effects of Antagonist Static Stretching on Agonist Performance.
Hmm.
This comes from a team of researchers: Mohammadmahdi Bahrami, Hiwa Rahmani, Duane C. Button, Andreas Konrad, and David G. Behm.
Quite the team.
And it was just published in the Journal of Sports Science and Medicine, the 2025 volume 24, pages 93 to 103. We'll have all the details in the show notes if you want to check it out yourself. This research team, they really wanted to know how different durations of this specific kind of stretching impact the muscle you actually want to perform.
Yeah, the timing is key.
Is there a magic number? An optimal dose that unlocks power? Or does it just, do nothing? Get ready, because what they found might just make you rethink your warm-up strategy.
Indeed. And, stretching has been a cornerstone of athletic routines for decades, right?
Absolutely.
Yet the scientific understanding of its immediate effects, the acute effects on performance, has become incredibly nuanced.
Right.
Historically, there was this simple belief: more flexibility always translated to better performance.
Seemed logical.
But in recent decades, that notion, particularly concerning static stretching performed right before activity, has been heavily challenged. This study, by meticulously examining varying durations in specific muscle groups, provides crucial new data to help resolve some of the contradictions we've seen. It's a vital piece in a complex puzzle.
Okay, let's unpack this a bit. We know, generally, that consistent stretch training over time can absolutely enhance your joint range of motion. That's widely accepted, right?
Definitely. Long-term flexibility gains are well established.
We've all felt that satisfying looseness after a good stretching session. But the key here is over time.
Exactly. What's truly fascinating is the distinction between that long-term flexibility and the acute effects. The conversation around performing static stretching, holding a stretch for a sustained period right before a high-performance activity, that's dramatically evolved over the last, say, 25 years.
How so?
Well, a significant body of research, including some really robust meta-analyses, has consistently shown that prolonged static stretching, especially when you hold a stretch for 60 seconds or more per muscle group, can actually impair your subsequent performance.
Impair, so make it worse.
Yes, exactly. We're talking about measurable drops in things like force production, peak torque, explosive power, even balance, and how well your muscles activate. Some key studies, like Simic and colleagues back in 2013, found deficits were smallest if stretches were kept under 45 seconds.
Okay.
But more recent work, like Warnicki and Lohman in 2024, highlighted quite significant impairments for 60-second stretches compared to just resting. So it's definitely not as simple as more flexible equals better immediate performance.
So if stretching the target muscle for too long can actually hurt your performance, that begs the question, what about stretching its antagonist, the opposing muscle?
Precisely.
This is where the idea gets really intriguing, right? Think of it like this. Muscles often co-contract or co-activate. Your biceps, for example, might slightly activate even when your triceps are extending your arm.
Like a braking effect.
Exactly, providing a kind of braking effect to control and stabilize the movement. So the theory is, if you could somehow reduce that braking from the opposing muscle,
Dial it down a bit.
then your working muscle, the agonist, could theoretically perform with greater force, power, or speed. It's like taking your foot off the brake while hitting the gas, maybe.
That's the analogy, yes. And that's precisely the central question this whole line of research is trying to answer. Can we strategically stretch an antagonist muscle to reduce its braking effect and, in turn, enhance the agonist muscle's performance?
So does it work?
Well, that's where it gets tricky. The existing scientific literature has been surprisingly contradictory on this point. It's not a clear-cut yes or no. See, on one hand, some studies have indeed reported positive effects. For instance, Elliott and Massey in 2020, they saw a significant increase in bench press power after just 30 seconds of static stretching. They targeted the shoulder adductors and protractors, those are the antagonists to the big chest muscles.
Okay, 30 seconds isn't very long.
No, And other research, like Sandberg et al. In 2012 and Wakefield and Cottrell in 2015, used longer durations, maybe 90 to 120 seconds of antagonist stretching on hip or knee flexors. They showed small to moderate increases in vertical jump height and isokinetic torque.
So longer durations worked there.
In those cases, yes. Even a shorter 40-second stretch of the pec major was linked to increased training volume and activation of the agonist muscles in seated rows in a study by Miranda et al. Back in 2015. So there's definitely evidence suggesting it can work sometimes. But then on the flip side, you have studies that found absolutely no substantial improvements.
The plot thickens.
Right. Jones and Humphrey in 2018, for example, reported no significant changes in vertical jump after 40 seconds of antagonist stretching. And Serafil-Glue et al. In 2017 found no increases in knee extension peak torque, even with a really long 240 seconds of antagonist stretching.
Wow, 4 minutes. And still nothing.
Still nothing significant. And when researchers looked at electromyography, EMG, which measures muscle activation, well, some studies showed increased agonist EMG activity after antagonist stretching, which often correlated with performance gains, but others detected no change whatsoever.
So it's all over the place.
It really is. This inconsistent picture strongly suggests that the effects might be incredibly specific to the muscle group, the type of exercise, and crucially, the exact duration of the stretch.
Okay, so with all that contradictory evidence, it sounds like researchers really needed to get to the bottom of this. Like, was there an optimal dose of antagonist stretching, or was it all just a wash? That's why this new study is so important then. Most previous research tended to focus on just one stretching duration, say 30 seconds or maybe 90 seconds.
Right, they pick a number.
But this new team, they set out to explicitly compare varying durations of antagonist static stretching. They wanted to pinpoint if there was an optimal dose for performance improvement, or, like you said, if it just makes no difference at all. They were really testing that braking effect theory directly.
Precisely. That was the central question driving their investigation. They weren't just looking for any effect. They went in with a very specific prediction, a hypothesis.
Oh, was it?
They hypothesized that while all the antagonist dorsiflexor static stretching durations, they tested 40, 80, and 120 seconds, could potentially improve plantar flexor performance and jump metrics. They anticipated a greater positive impact with the longest duration, the 120-second stretch.
Why the longest?
Their reasoning was that a longer stretch would lead to a more significant reduction in the antagonist muscle's force and co-activation, sort of relaxing that brake more, thus freeing up the agonist muscle. It was a very targeted attempt to find that sweet spot, if one actually existed.
That's a clear hypothesis.
Yeah.
Makes sense. So how did they go about testing it? What did their experimental setup look like?
To do this rigorously, the team recruited 16 healthy, physically active participants, 10 males, 6 females, all between 18 and 40, and importantly, they all regularly did strength training.
So people used to exercise?
Yes, not beginners. And they ensured strict pre-testing protocols, no intense activity for 24 hours prior, and participants had to abstain from alcohol, smoking, and caffeine for 12 hours before testing.
Standard stuff for these kinds of studies.
Right. And the study used a meticulously designed randomized crossover design. This means every single participant went through all 4 testing conditions, each separated by 48 to 72 hours of rest.
Okay, what were the 4 conditions?
So there were 3 different antagonist static stretching durations. 40 seconds, which was just one sustained stretch, 80 seconds achieved with 2 40-second stretches with a brief rest, and 120 seconds using 3 40-second stretches. Plus, crucially, a control session where no stretching was performed at all.
Gotcha. And the crossover design means everyone did everything.
Exactly. Each individual essentially acts as their own control, which is great for minimizing individual variability in the results. It makes the findings more robust.
Okay, let's talk anatomy for a second. You mentioned dorsiflexors and plantar flexors.
Yeah.
Can you quickly break that down? Which muscles were they actually stretching, and which ones were they trying to boost?
Great question. So they specifically stretched the participants' dorsiflexors. These are the muscles on the front of your shin.
Okay.
They allow you to lift your foot upwards, pulling your toes towards your shin. In this scenario, the dorsiflexors act as the antagonist, the muscle group that opposes the main movement they were interested in.
The main movement was?
The main movement was powered by the plantar flexors. Those are your powerful calf muscles, the gastrocnemius and soleus.
The calves. Got it.
Right. They're the agonists, the primary movers, in actions like jumping, standing on your toes, or pushing off the ground. So the goal was stretch the shin muscles, dorsiflexors, to see if the calf muscles, plantar flexors, performed better.
How intense was the stretch?
It was performed passively. An investigator moved the participant's foot into maximum plantar flexion, basically pointing the toes down as far as possible until the participant reached their maximum point of discomfort. So it was a deliberate, intense stretch, not just a casual warm-up thing.
Okay, intense stretch on the shin, hoping for better calf performance. And what were they measuring? How do they actually quantify performance?
They were very thorough. They measured several performance indicators, all focused on the strength and power of those plantar flexor muscles, the calves.
Like what?
For muscle strength, they used a specialized isokinetic machine. This measured isometric peak torque that's force without movement.
Just holding it.
Right. And also isokinetic peak torque, which is force during movement at both a slow speed, 60 degrees per second, and a faster speed, 240 degrees per second. They also looked at total work output during those movements.
Okay, strength covered. What about jumping?
Then, for jump performance, they use something called the stiff leg drop jump, or SDJ. This specific type of jump is designed to minimize knee and hip bending, so it really isolates the work done by the plantar flexors.
Really focuses on the calves.
Exactly. And they recorded jump height, something called the Reactive Strength Index, or RSI, which looks at how quickly you can generate force and also peak power during the jump.
Makes sense. Anything else?
Yes, finally, to understand what was happening at the neural level, they used electromyography, or EMG. This measures the electrical activity of the muscles.
Muscle activation.
Precisely. They looked at the soleus, one of the main calf muscles, and the tibialis anterior, a key dorsiflexor on the shin, in the dominant leg. This gives insight into how much the brain is actually telling those muscles to fire during the tasks.
And it's worth mentioning the timing, too, right? You said the jump was tested immediately after stretching.
That's right. The stiff leg drop jump was tested immediately after the stretching intervention finished, and then the isokinetic and isometric strength tests followed about 5 minutes after the stretch.
So capturing those immediate acute effects.
Exactly.
Okay, so after all that rigorous methodology, the specific muscles, the different durations, the careful measurements, what did they actually discover? What's the big takeaway for us?
All right, now here's where the primary outcome of this deep dive becomes quite clear, and it's quite a definitive finding, really.
Okay.
The study found that the different durations of antagonist dorsiflexor static stretching, whether it was for 40 seconds, 80 seconds, or 120 seconds, did not significantly influence any of the measured performance metrics.
Wait, none of them?
None of them significantly. We're talking no statistically significant change in pre- to post-intervention plantar flexor isometric peak torque, isokinetic peak torque at either speed, total work, or any of the stiff leg drop jump measures like height, reactive strength index, or peak power.
Wow, so it just didn't work.
It directly contradicted their hypothesis that the longer durations would show greater benefits. Essentially, for these specific muscles and these specific durations, stretching the antagonist, the shin muscles, didn't move the needle on calf performance.
Okay, so no matter how long they stretched the shin muscles, it didn't really help their jump or their calf strength. That's a pretty straightforward no, which is actually a really important answer in science, isn't it?
Absolutely. Finding no effect is just as valuable as finding an effect.
But then you mentioned something earlier about testing effects. What was that all about? Because that sounds like a different twist.
Ah, yes, this is where it gets really interesting and provides an even deeper insight, perhaps, than just the stretching results themselves. While the specific stretching durations didn't cause a direct beneficial change, the data revealed a crucial main effect for time.
Main effect for time. What does that mean?
It means that when they looked at performance across all the testing sessions, regardless of the stretching condition, performance tended to decrease slightly from the pre-test measurement to the post-test measurement.
Even in the control group, the ones who didn't stretch at all.
Yes, that's the key. Even the control group, who performed no stretching, still showed a slight dip in performance over the course of the testing session for some measures. Across all conditions combined, the 40-second stretch, the 80, the 120, and the no-stretch control there was an overall decrease in certain metrics. For example, fast and slow isokinetic peak torque decreased by around 5.9% and 6.6% respectively.
Okay.
Fast isokinetic total work dropped by about 5.1%, and all the stiff leg drop jump measures saw declines, with jump height decreasing by about 2.7% overall.
Whoa, okay, hang on. So even with no stretching, performance still went down a little bit just from doing the tests.
Yeah.
What does that tell us? That's genuinely counterintuitive for most people, I think.
Exactly. And that's why it's such an important finding. This observation points strongly towards what researchers call testing effects.
testing effect.
It suggests that the repeated execution of these maximum effort tests themselves, even with the designated rest periods between them, might have induced a slight fatigue or perhaps some kind of neural adaptation in the participants.
Just doing the tests tired them out a bit.
Essentially, yes. Or changed how their nervous system approached the task on the second attempt within the session. This led to a general decline in performance over the session, regardless of whether any stretching was performed or not. It's a crucial reminder that sometimes the very act of measuring can influence the results you get. And we saw this reflected in the EMG data too. There were significant reductions in the activation of the soleus muscle, the calf muscle, observed not only after the 80-second and 120-second stretches, but also in the control condition.
So the muscle wasn't firing as strongly later in the session, even without stretching.
Correct. Which reinforces the idea that the repeated maximal contractions were likely fatiguing the muscles or altering neural drive over the course of that single testing session.
That's a huge aha moment right there sometimes. The act of testing itself is a variable you have to account for.
Fascinating. There was one other little nuance you mentioned about jump height specifically, comparing the stretching groups to the control group. Can you just clarify that point again?
Absolutely. So the study did note one specific finding regarding jump height. The 40-second and 80-second antagonist stretching conditions showed a small but statistically significant reduction in jump height compared to the control group overall, about 5.6% and 4.0% respectively.
A reduction. So stretching made the jump slightly worse in those cases. Compared to the control group, yes, when looking at the overall data. However, the researchers are very careful in their interpretation here. They point out that this was identified as a main effect for condition and not a condition by time interaction.
Okay, statistics. What's the difference mean practically?
Practically, it means the analysis essentially averaged the pre- and post-test jump heights for each condition and then compared those averages. To confidently say that the stretching itself caused a reduction from the pre-stretch measurement to the post-stretch measurement within those groups, they would have needed to see that specific interaction effect.
Ah, I see. So it's suggestive, but not definitive proof that the stretching caused the drop within the session.
Exactly. Given the lack of that interaction effect and the presence of the overall testing effects we just discussed, they conclude it doesn't provide robust evidence for a clear stretch-induced impairment in the same way we sometimes see with prolonged agonist stretching. It's another layer of complexity, another reason to interpret results carefully.
That makes perfect sense. Wow. It really sounds like this study didn't just give us a no answer to the specific stretching question, but it also, maybe more importantly, illuminated a fundamental challenge in exercise science research itself.
Precisely. And if we connect this back to the bigger picture, these specific findings that this particular dorsiflexor antagonist stretching protocol had no significant effect actually align quite well with several other studies that also found no significant changes in peak torque or EMG after various antagonist stretching protocols.
Okay, so fits with some other research.
Yes, but then the question remains, why do some studies show positive effects while others, like this one, don't? The discrepancies in the literature likely boil down to a few key factors. First, and perhaps most importantly, muscle specificity and size. It matters hugely which muscles you're stretching and which ones you're trying to boost.
Oh, so?
In this study, remember, they stretched the dorsiflexors, the shin muscles. These are generally smaller and less powerful than the plantar flexors, the calf muscles they were trying to boost.
Right, calves are much bigger.
Exactly. This force and size imbalance might mean that stretching the dorsiflexors simply has less influence on the powerful plantar flexors compared to studies that stretched much larger antagonist muscle groups, like stretching the hamstrings to improve quad performance or stretching the back muscles to improve chest press. The braking effect of a smaller antagonist might just be less significant to begin with. Second, the stretching protocol itself is critical. The method, the intensity, how long it's held, it all matters.
Like you said, this was maximum point of discomfort.
Right, which is quite intense. Some previous studies that reported positive effects use terms like mild discomfort, though admittedly that term often isn't precisely defined in the methods. So the difference in intensity, or even the exact technique used to apply the stretch, could certainly lead to different physiological responses.
Makes sense.
And finally, the researchers themselves acknowledge a potential methodological challenge. They noted that effectively stretching the tibialis anterior, which is a primary dorsiflexor, just by passively moving the foot into plantar flexion can be technically tricky. It's possible the stretch wasn't optimally targeting that muscle in all participants, which could also influence the results. All these subtle differences between studies can lead to dramatically different outcomes.
That's incredibly insightful. It really shows how careful you have to be comparing studies. So, okay, let's bring it back to the practical side. For you, the listener, the athlete, or just the curious mind tuning in, what does this all mean for your pre-exercise routine? What's the actionable takeaway from this deep dive?
Well, the practical implications here seem quite clear, at least for this specific type of stretching involving these muscle groups. If you're incorporating 40, 80, or maybe even 120 seconds of dorsiflexor static stretching that's stretching your shin muscles into your warm-up, this study suggests it's unlikely to significantly enhance nor impair your immediate plantar flexor performance.
So for your calf muscles.
Right. Whether you're aiming for more strength, more power, or a higher jump immediately after, this particular antagonist stretch, performed for these durations, appears to be largely neutral for those outcomes based on this evidence. So if you're doing that specific stretch purely hoping for an immediate performance boost for your calves, this research suggests you probably won't get it.
Okay, so it's probably not harmful in this context, but it's also not the secret weapon some might have hoped for. Fair enough. And beyond the stretching itself, that whole revelation about testing effects seems incredibly important, doesn't it? For anyone in exercise science or even just someone trying to track their own progress.
Absolutely. I think that's a really key takeaway. This raises an important point that extends way beyond just stretching. The consistent observation of these testing effects serves as a crucial reminder for anyone interested in exercise science, or really anyone who tracks their own fitness data. It highlights that the very act of repeated high-intensity testing itself can induce subtle fatigue or adaptation. This makes it absolutely vital to carefully consider how experimental design or even just how you structure your own training log and testing might be influencing the results you see. It encourages us all to look beyond simple cause and effect relationships and understand the full dynamic of how our bodies respond, not just to an intervention like stretching, but also to the demands of being tested or pushed. It's a powerful lesson in scientific humility and the need for careful interpretation.
So there you have it. Our deep dive into this latest research on antagonist static stretching suggests that, well, at least for your douche flexors and plantar flexors, stretching for 40, 80, or 120 seconds might not be the game changer you're looking for in terms of an immediate performance boost.
Seems that way based on this data.
And perhaps even more importantly, that fascinating phenomenon of testing effects reminds us to always consider the full picture, including the demands of measurement itself when we interpret scientific studies or even our own athletic progress.
And this research really prompts us to consider, doesn't it? How much of what we assume about our warm-up routines or even our training adaptations is truly based on robust evidence? And where might these muscle-specific interactions or subtle fatigue, or even as we saw here, the sheer demands of testing, be silently influencing our athletic outcomes? It's really a powerful call for continued critical thinking and, frankly, curiosity in our approach to training and understanding performance.
Well said. We highly encourage you, if this piqued your interest, to read the full article. Again, it's The Acute Effects of Antagonist Static Stretching on Agonist Performance by Bahrami and colleagues, published in the Journal of Sports Science and Medicine. You can explore all the details and references for yourself. And, of course, if you enjoyed this deep dive, make sure to follow our channel and turn on those notifications so you don't miss our next exploration into fascinating